Everyone. This presentation to talk about one algorithm from nature-inspired algorithms that can be used for optimization purpose. So the entire presentation is going to be about an algorithm called mother tree optimization algorithm, which we have proposed, me and Dr. Mawhoub. Actually, we are not going to talk about the different categories for optimization algorithms, but in a brief, we have exact methods and we have approximate methods. And under the approximate methods, we have a subcategory called nature-inspired algorithms that mimic the behavior of biological phenomena and natural phenomena, and we have other categories. So this algorithm, which we call it mother tree optimization algorithm, is one of the nature-inspired algorithms. And what we are going to cover in this presentation, we are going to give a brief introduction about the biological background of the phenomena that we have built the algorithm on. Then we are going to talk about the mother tree optimization algorithm, and we are going to talk about the offspring topology that we have used. We proposed a new topology, and the topology is a way of communication between agent or particles in the population. And then we are gonna explain how we are gonna update the position of each agent in the population. And we are going to talk about the MTO, which is another variant of mother tree optimization algorithm that we have proposed using climate change. Then we are going to talk about the experiment that we have conducted and some results and conclusion about the presentation. So the biological background, actually we built this algorithm on the relationship between Douglas fir trees, as we can see in the picture, and mycorrhizal fungi network. So the mycorrhizal fungi network is linked to the roots of the Douglas fir trees, and this connection can facilitate the transferring nutrients between mycorrhizal fungi network and the trees. So the mycorrhizal fungi network helps the tree to support with the nutrition, and by the same way the trees supports the mycorrhizal fungi network with the carbon. So the tree itself has what we call it like cooperative system. Cooperative system helps the tree to communicate, exchange different essential nutrition between other parties in the region. So as we can see here, this is the cooperative system for the Douglas fir trees. So we have the cooperative system, and we then divided the system to 3 subsystems. So the cooperative system had a recognition system and measurement system and defense system. So the recognition system actually to distinguish between the trees in the search area. So the Douglas fir trees has the capability to recognize their kin from other trees in the same region. And the measurement subsystem helps the Douglas fir trees to distinguish between which is the better mycorrhizal fungi network. So the amount of nutrition that the Douglas fir trees that can receive from different mycorrhizal fungi network can be evaluated, and then the Douglas fir trees can decide which fungi can deal with and start receiving nutrition from this fungi, and or helping the Douglas fir tree to receive nutrition from this fungi. through these fungi and support these fungi with a higher number of carbon. In addition, the system or the cooperative system for the trees has a defense mechanism that protects the root system of the trees against pathogens and helps the trees to survive longer. So the way that we built the mother tree optimization algorithm, the same as any other nature inspired algorithm, we firstly initialize the population with random or by any specific way in the search area, and then we set some rules for this agent to follow so they can update the position, and we update the position in two different ways. The top mother tree, which is the best or the global solution in the population, will update the position in a random way. However, the rest of the population is gonna be updating the position based on some equation that we are gonna show very soon. So the way that the agents in the population are communicating together, that firstly we rearrange the agents in descending order. It means that the first one or the first particle in the population has the highest nutrition, the highest number of nutrition, and the last one or the last agent in the population has the lowest number of nutrition. So as we can see, every and single agent in the population can feed, but it's not it can or cannot, like most of them they can feed at most NOS number of trees. So the NOS, we call it offspring, and this NOS is equal to NS divided by 2 minus 1. So assume that we have 6 trees, so we are gonna have NOS equal to. So it means that every trees can feed the next or the following 2 trees in front of this agent. So NOS N1 we can feed N2 and N3 and so on. However, we have another rule that says feed the following NOS or none. So if you have in the front of you a number of trees is lower than the NOS, so you cannot feed anyone. What I mean, in the previous example that we just gave, if we have 6 trees, so if we are here and we have only 1 tree in the front of us, so we cannot feed any tree in the population. So we feed the full or the NOS, the total number of NOS or none. And based on this classification, based on this way of communication, the population is divided into 4 groups: the top mother tree, first partially connected trees, and fully connected trees, and large partially connected trees. And these groups, the first 3 groups, like in the top mother tree and fixed first partially connected tree and fully connected trees, like all of them, they can feed, like they are feeders, and the last group is non-feeder, so this group cannot feed anyone in the population. So this is the way that the agent in the population will update the position. The top mother tree in the population, as we just explained here, this is the top mother tree, which is the first or the agent that has the highest number of nutrition. So this one will update the position in a random way in 2 levels. So it will go in a random direction, and if the new position after S1 has a higher number of nutrition or higher fitness than the original or the current current fitness for the top mother tree, so it will go to another step, which we call it mycorrhizal fungi network signal. So it will go for S11 and S12 and S13. So every time and we'll search in this area for a better solution. However, if after S1 the value has a lower number of has lower fitness, so it will not go to further for S11 or S12 or S13, it will go in a random direction, and it will go to the next cycle. Here in the other groups, so it will like follow these equations that we already proposed, and this equation has like a mathematical derivation, but the time of the presentation will not allow for us to explain more details about these equations. And after we proposed the basic algorithm, the mother tree optimization algorithm, we find in some cases that the mother tree optimization algorithm is stuck in a local minimum solution. That's why we thought about another variant of MTO, and this is what we call the MTO with climate change. And this new variant, actually we will use the basic algorithm like the MTO as we just explained, but we just will add a couple of stages in the algorithm: the mutation and the distortion. The mutation, actually it's an elimination, like we will eliminate the least healthy agents in the population. I mean the agents that has lowest fitness value, and we will add to the population random agents instead of the ones that we eliminated. And in the distortion, we will deviate the rest of the population from its position. And this picture will explain clearly what we have done. So assume that we have 10 agents in the population. So the one we marked red, we will eliminate it because this is the least healthy or has the lowest fitness value, and we will add 2 green random agents in the population. Then in the distortion stages, in the distortion stage, actually what will happen, we will just eliminate, we will just deviate the rest of the population. As we can see here in this picture, for the one that has red, green and blue, the rest of the agents just deviated from the green to from the blue to green. Blue is the initial position and green is the final position. And to evaluate the performance of this algorithm, we conducted an experiment to compare the mother tree and its variant with some other variant of PSO that already has been published by Dorigo, the inventor of anti-colony algorithm. So we will, the objective of our experiments to compare the number of function evaluation of the algorithm or the proposed algorithm with other algorithms at different quality solution. And we have used the 30 dimensions for all benchmark functions, and the benchmark function that we have used, it's a very well-known benchmark functions that have been used to evaluate different algorithms or variant of algorithms. And the number of runs, we used 100 runs for every and single benchmark function, and then we calculate the best and standard deviation and the average. So regarding it with the setting of the algorithm, so first we tried 20 and 60 agents. Regarding to the parameters of our algorithm, which is MTO and MTOCL, we recommended some preliminary, based on some preliminary experiments that we have conducted. We recommended some values for these parameters. And this is the algorithms that we are comparing with the PSO. All of them, it's based on the PSO, particle swarm optimization algorithm, but different variant of this algorithm. So, and this is the benchmark function that we have. We are comparing. We are conducting the experiment, our experiment on, and some of them, they have a very large number of local minimum solutions to test the algorithm that can reach the global solution and escape from the local minimum solutions. So these are the results actually that we received. The MTO couldn't solve for the first benchmark functions. Actually, the MTO couldn't solve the problem, and that's why we thought about introducing a new variant of this algorithm, because in some cases the MTO itself cannot solve the problem. So we introduce the mutation distortion stages to solve the problem. And as we can see here, the MTO with climate change CL can solve the problem. In the second one, as we can see, we achieved better performance than the best PSO variant, except for when we increase the quality, the solution quality, like for the second benchmark functions, we start with 0.077 quality solution quality, and until we reach it to 0.01, and this is when we increase the solution quality of the problem, the difficulty of the problem increases. So the quality, the canonical PSO variant using ring topology, solving using fewer number of function evaluation than other variants, even our algorithm, when we increase the solution quality to 0.001. However, we solve it in the one the rastering. We solve it in almost 2 cases better than the other PSO variants. And this is when we increase the solution quality to 1, we solve it using MTOCL with a number of function evaluation actually lower than the one that has been solved using PSO using HPSOT 1/6. Like we solve it in 100,000 iteration, and the best PSO solve it in 600,000 iteration. And this is the rest of the benchmark function and the results. So like in general, we see that the MTO can achieve good solution with respect to other particle swarm optimization or other variants of particle swarm optimization. And this is just a simulation for run length distribution on a couple of benchmark functions to just simulate this graph. They use it to demonstrate of developing the probability of finding the optimal solution. And as we can see here, the dotted for the one that without climate change and the solid for the one with climate change, we can see actually the probability of finding the solution is really increased when we use the MTO using climate change. However, the MTO in some cases exhibits strong stagnation, as we can see here, and this is different quality solution. This one 15, and this one 20, and this one 30.3. So when we increase the solution quality, as we can see here, the MTO has a really stagnation problem. But when we increase this is when we use the 20 agents in the population. But when we increase the population to 60 agents, MTO achieved a good solution with respect to MTOCL. This is another one to show that even if, like here in the first one, like in the first column in the left hand side, with different quality solution, when we increase the quality solution, the stagnation problem for MTO increased, but MTOCL, as we can see, it solves the problem with a probability 1 in each case. However, in this case, when we increased the number of agents from 20 to 60, actually we still have the same problem that we have still stagnation with MTO. But MTO-CL is pretty good and it achieves better results than even MTO. So the conclusion of the presentation, we propose a new NI nature-inspired algorithm that we call it MTO for solving continuous optimization problem, and we published this algorithm, and we already released another version of MTO for discrete optimization problem, and we already published this one, and we implemented this algorithm on a neural network to tune the weights, and we already published this application. So in general, our results show that the MTO and MTO-CL variant achieve promising results for a suite of commonly used benchmark functions compared to several PSO variant. So MTO algorithm and its variant deliver high accuracy with a fewer number of function evaluation on a suite of well-known benchmark functions. And thank you for watching this presentation, and any question. Thank you.